I don't know, and and then you can put it on like a resume and stuff, like attended this conference. What are you talking on, Cormac?
The rock sequences of poly trees.
Cool. Does that work with Cyber? Nice. That's very cool. Yeah, will you please definitely send me like when and where, what room and stuff like that? Cool. And it's kind of like an excuse to like just not come to school for one day. It's like, go there, I don't have to put on shows. Just like, kind of go there and be anonymous. I'll drive separate, just kind of like hide out. Maybe I'll see you there. I'll see you. Maybe I'll see you there. I hope so. I hope I see you there. We can make sure we see each other there, all of us. All right, friends, so enough of that. Mild pressure. Do you have any questions on that sign-up that's due Wednesday? Has anybody tried any of it? You have? Yeah. So like what kind of, are you finding any struggles, like understanding even what I was asking? Or?
I feel like it hasn't been like, I do have a couple questions actually.
Yeah, cool.
But the question that I struggled like the most with, that I'm still like not really able to figure out, is the Cantor set one.
Yeah, let's talk about that a little.
I can't find like a series or like a sequence to like generalize it so I can figure out like.
Yeah.
Because I know what it should do, I just don't know how to explain that it should
definitely
do that.
So I asked for the length, the final length.
Of the remaining pieces.
Did I ask for the dimension or not?
Yeah.
Okay, we better talk about dimension. So I talked to you about dimension, but I didn't talk to everyone. So this is in relation to that Cantor set problem. And, Liv, and you missed me saying this, please make sure I recorded all the stuff you got back, make sure it was recorded, like corrections and at some point, thanks. So the Cantor set has what's called fractional dimension. And this is actually where the term fractal comes from. If you've ever heard the term fractal, you've ever seen cool, trippy images, zooming into them. If you've been in my Calc 2, nobody here was in Calc 2 with me, were they? Were you? Did we zoom into the Mandelbrot set? Yeah, we did. So at some point we have to. I feel like in Calc 3 we need to, but it just never comes up. Maybe we can in here because we're talking about it. So what is a fractional dimension? Well, there's lots of different ways to even think about dimension. Mathematicians have spent a lot of time thinking about this. And there's at least 3 that I can think of ways to measure the dimension of something that I can think of. But the one that is pertinent right here is this scaling definition. So, and I'm gonna do some weird stuff. Let's take a point. So like just what's your inherent understanding of the dimension of a point? What's its dimension? So dimension is think of how many degrees of freedom in movement you have. There's no movement here, so 0 dimension. We usually think of a point as something with no width or any size to it. So dimension we think of as 0. Now how about a line? Now a line has dimension 1 because there's one axis of motion I can move in. I've got 1 degree of freedom. So the dimension is 1, so that's a line. And then a square, what's its dimension? 2, because you can move left, right, up, down. It's 2 by 2, it starts. All this stuff feels really inherent and you don't think about it unless you're a math person. And then a cube has 3 dimensions, or dimension 3. But let's talk about how we can also get these same numbers through this different way. Like this right here is almost just kind of intuitive, like, oh, I learned this, so this is what it is. So the scaling definition says this: you take your object and you multiply it, you scale it by some factor. So for us right now, we're gonna do 3. It doesn't have to be 3, but it'll make sense for the Cantor set if we do 3. So I scale it by 3. If you multiply something with 0 width and 0 height by 3, how much does it change at all? I mean, what's 0? What's 0 times 3? 0. Right? So the length and width don't change. So this thing stays the same. And I'm going to write over here that I multiplied by 3, and I ended up with 1 copy. So this is number of copies of the original. And this 3 was the scaling factor. And the exponent on 3 is 0, because 3 to the 0 is 1. This is where we're going to find our dimension. And let me do a couple more so you kind of see what I'm talking about. So let's take a line. I'm going to take a line segment. You can even add some units to it if that would help. And I'm going to multiply it, I'm going to scale it by 3 in every direction that I can. So when I scale it by 3, it turns into a line 3 units long. Doesn't change the width because it never had, or height, it never had height. So it turns into 3. So when I multiply by 3, scaling turns into this. How many copies are there? How many copies of the original are inside there? 3. Do you see it? There's the first copy, there's the second copy, and there's the third copy. There's 3 of these that now live inside there that make that up. So I have 3 copies, that's number of copies. I scaled by 3, and what power do I have to raise 3 to get that? 1. So dimension 1. Let's try this one. I take a cube. Now it starts to get a little more interesting. Take a cube, and let's just assume that it's got unit sides, 1 and 1. I'm going to scale it by a factor of 3. So this one's actually going to scale this way and down. So it's going to become a 3 by 3 square. How many copies of the original are there? 9. See that? Because each of these is a unit square. So here we have 9 copies. And so 9 copies equals 3 to what power? 2. And that's the dimension that we associate with it. Let's do this guy, so you believe me. Take my unit cube. Scale it by 3. And I get a bigger cube. Kind of a cube. But this cube is scaled by 3 in every dimension. How many cubes are in that? How many unit cubes are in the scaled cube? 27. All right, we've got 9 on each layer, 3 layers. There's 27 copies of the original. So 27 copies equals scaling factor to what power? 3. That's the dimension of the original object. So now so that also you're starting to see like, this seems kind of phony. How's this going to help us? Well, we can use this scheme, and this is a totally legit way to measure dimension. And it coincides with the other measures when we have simple things to measure the dimension of. But let's start with the Cantor set. And I also want to note that the scaling by 3 doesn't have to be the only way. Watch what happens. If I take this cube and I scale it by 2, then I'm going to get, what am I going to get here? 2 by 2 by 2 cube. And how many copies are in there of the original? In this 2, 8. So number of copies equals scaling factor to what power? Third. So again, I get the same dimension even if I use a different scaling factor. The reason we're using 3 is because we want to now do this Cantor set. And some things you've got to pick the right scaling factor for, which is a hint for your homework. So I'm going to take the Cantor set. Remember how we built that? First we took a unit interval, we remove the middle third. So that's 1/3, 2/3, and these are closed intervals. So we're removing open pieces. Now remove the middle third here. Open middle third. So that's like 1/9, 2/9. So how many ninths is that? That's 8/9, 7/9 right there. And then keep on doing that forever and ever. And what you're left with is that Cantor set then. So let's take this and multiply it by 3. Now look what's going to happen. This piece here was originally 1/3 unit long. Then there's a space of 1/3 where nothing happens, and then another 1/3 where the second identical piece occurs. So when I scale by 3, this first piece actually becomes, instead of 0 to 1/3, it's 0 to 1. Instead of 1/9, that's 1/3. Instead of 2/9, that's 2/3. That's just this first piece. Now a big old gap, a gap of 1 unit, because this original gap was 1/3 of a unit. And I got the exact same thing over here. And so this turned into what? 2, this is 3, and then these are the appropriate things in between. Each one of those, and each one of these still, since this process was infinite, has all these infinitely many holes that we cut out. These infinitely many pieces are missing. There's pieces in here missing. How many Cantor sets are there? How many copies of the original, exact copies of the original? Got this, the Cantor set is both these pieces. Here's 1 copy. That's exactly like the original Cantor set. When I multiply this piece by 3, scale it by 3, it turns into the whole Cantor set. When I scale this one by 3, it turns into the whole Cantor set. So there's actually this copy and then this copy. So there's 2 copies when I multiply by 3. Because of that weird hole removal stuff. It's a weird thing. So what we get is I've got 2 copies equals scaling factor, and this must be the dimension here, whatever that exponent is. How do I solve for that exponent? Majors. We're not doing real analysis here. We're doing MT453. No pressure. But how do I solve for D?
Take the log.
There we go. Take the log. You got a variable in an exponent, you take the freaking log. Doesn't matter what log. Take log base 10, log base 2. Log base E is generally just the default. So I'm going to take the natural log of each side, and that should hold true. Now what, Christian?
You can bring the exponent forward.
Yeah, so now I can turn it into a multiplication. Bring that exponent out front. So I've got natural log of 2 equals D times natural log of 3, and then I solve for D, and I'm not going to, I know you know this next part, so I'm not going to even pretend like I need to ask. The dimension is that number. Does somebody have a calculator for us? Could someone please crank out natural log of 2 divided by natural log of 3? Approximately. I feel like it's 6 something, but I don't know. It's been a while. Thank you. That's good enough for us. Yeah. So it's somewhere between a 0 dimension thing and a line. It's somewhere between a point and a line, tending a little bit more toward the line, right? Here's 0.5 dimension, so it's kind of in this half over here. So it's more like a line than it is a point, but it's neither. It's somewhere in between. It's a fractional creature. And you can do this with lots of different objects. Anytime you have something that's a fractal, you can do this process with it. Let's actually, yeah, while we're here, you know what, we're just gonna freaking do. There's like a Cantor rug that we can make. So if I take a cube, or square, and then I remove the middle third square, so kind of cut each side into thirds like this, and then cut the middle square out. And then repeat this process with every little square that's left. So check this out. So I took the original square, I'll just color it in, the stuff I'm blocking out. Now I've got 8 different squares. I'm gonna block out the middle third of each one of those. And I'm gonna what am I thinking of? I'm going to continue this process forever and ever. Each one of these is made up of 8 little subcubes. You see the little 8 subcubes? Like that? And then I'm gonna pull out that centerpiece and that centerpiece. And I'm gonna continue to do this forever. I think this might be called like a Sierpinski carpet or something like that. But just imagine this process going on and on forever. Let's figure its dimension. So let's scale it by 3. That seems like an okay thing here. If I scale this by 3, let's see, here's the original, 0 to 1, and then this was 0 to 1 on that axis. So if I scale it by 3, what are we gonna get here? So this will be 3, this will be 3, and then this was 1/3, this was 2/3. So when I come here, that's gonna be 1 and 2. That's gonna be 1 and 2. And this, like, the picture's not great, the way I'm drawing it. But the middle picture, or this big square that was in the middle, now that's just bigger. This dark square that we took out, that's just bigger. And then everything's a little bit bigger, but since it goes on forever and ever, there's still all the detail that I have there. How many copies of the original do I have now? 8 copies. Do you see that? That I could blow this up. There's 8 little copies because that middle one's missing. So I've got 8 copies equals the scaling factor times the dimension. So let's just go straight to it. It's natural log of 8 over natural log of 3. And we actually have enough information to kind of figure this out, because this is natural log of 2 cubed over natural log of 3. Do that exponent trick. It's 3 times natural log of 2 over natural log of 3. And natural log of 2 over natural log of 3 was the dimension of the Cantor set. So it's like 3 times that. So it's approximately 3 times 0.63, and that is approximately 1.89. So it's almost a 2-dimensional object, but not quite. It's missing enough substance to not make it fully there. But it's definitely closer to a 2D thing than a 1D thing. So that's fractional dimension. So the problem I gave you, this is what we need to talk about in probably several ways, was I said, now take a Cantor set, just the 1D one. If you want to go crazy, you could do the 2D and 3D versions if you really, like, were motivated. And you'll only get just personal glory for it, and I'll applaud you. It might be worth something. Tiny bit. The personal glory is the part we do anything for in math. The odds of any of us being famous mathematicians is low. Not impossible. You all have a better chance. I'm already, it's like it's over for me. This is like whatever fame I could have had has passed long ago. You could all still be famous. But it's a hard game to be a famous mathematician. I want to be one of those like popularizers, like a Neil deGrasse Tyson of math. We need one of those. I don't think we have that. Anyway, so your generalized Cantor set, I said start with an open interval 0 to 1 and remove the middle alpha So we're gonna take a number between 0 and 1, and we're gonna remove that from the middle. Let's kind of walk through this a bit together. So I pulled out a piece of length alpha. Let's figure out the coordinates here, and like how much is left. So right now, how much is left? What portion is left after that first removal? We'll call this C0, what's that? Here's C1, step 1. How much is left? How long is what's left?
0, 1 minus alpha.
What was the first thing you said?
It'd be like, could you do the interval of 0, 1 minus alpha?
Yeah, which is just like 1 minus alpha. Yeah, exactly.
Oh, yeah.
So the total length was 1. I think you all were thinking I was like looking for something much deeper than that. This was 1 unit. I pulled out a piece length alpha, and so this is what's left, 1 minus alpha. How do we figure the coordinates of these points right here? So this is still 0, this is 1. How can I figure out the coordinates of those points?
We kind of figured you do like 1/2 and then subtract like alpha over 2 or add
Perfect.
alpha over 2.
Yeah, that's perfect. So each of these, if this is the 1/2 mark right here, then we pulled out alpha over 2 on that side and alpha over 2 on that side. So this coordinate here would be, there's lots of ways to write it, but 1/2 minus alpha over 2 is pretty easy. And then this piece here is 1/2 plus alpha over 2. Is that what you were saying,
Yeah.
Christian? Yeah,
Yeah.
that's a good way to do it. So now I've got those endpoints. And I'm going to continue this process. It's not super important that you know these endpoints, but you want to keep track of what you've removed. So let's make a little table here. Removed. So what, and I was just asking this just to like make us think about it. So for the first step, we removed alpha. Might be a third, might be a normal Cantor set, might be something else. On the next step, how much am I going to remove? So I've got these 2 pieces left here. 0, 1, this was 1/2 minus alpha over 2, this is 1/2 plus alpha over 2. Now I remove the alpha proportion. Remember how this worked? Now I'm scaling down. I'm actually removing alpha squared from each of these pieces. Remember how that worked with the Cantor set? First we removed a third, and then we had these 2 pieces, and we removed a 1/9 from each one of those. So that's what we're going to do again. We're going to remove, well, is that right? Let's see. Are we removing an alpha? Yeah, of course we are. I think. Let's see how long this whole thing is. So this whole thing is 1/2 minus alpha over 2 units long. Times a third, times an alpha gives me alpha over 2 minus alpha squared over 2. So how much? So that's how much we're removing from there. And then we remove that same amount from here. So let's see, if I remove that much from here, and then that's the same length, so I remove the same amount from there. I've removed alpha minus alpha squared at this point. So this is, because there's 2 of those. Wait a second. Let's do this with the 4th. Let's do this with alpha as a 4th and just make sure my reasoning that I want to use is going straight. So we've got 0 to 1. We remove the middle quarter. So here alpha is a quarter, so this is going to be 1/2 minus an 1/8. So that's 3/8. And then this must be 5/8. Check me out on the math there. Does that seem right? Because 4/8 is right in the middle. Got an 1/8 on either side, so I think that's right. So now we're going to remove the middle alpha, the middle quarter of this thing. And I guess what I was thinking in my head is, oh, that must be 1/16 that we'll remove from each of these. But let's just double check. So if I took this thing here and I took 3/8 and I multiplied it by a quarter, so I took a quarter of its length, that gives me 3/24, that's 1/8. So I'm gonna remove 1/8 from here. Does that seem right? So why isn't it 1/16? 3/8, 1/4. This.
8 times 4 is 32.
Thank you. Okay, thanks. Yeah, because I didn't multiply properly. So yeah. So like I'm giving you shit about logs, and like I fucked this up. So 3/32 is removed from there. Huh. That's not 1/16. Then we do it again from here. Let's do it again from here. So from there, same amount, I would be removing, oh, this might be a little more complicated than I was originally thinking. But it's still okay, we can still handle it. So I remove twice this much. So times 2, once here, and so that's 6/32, and that's 3/16. It's more than I thought it would be. Is that right? I might put this problem on hold and just work it myself until I understand what the hell needs to happen here. And this might be, I was doing some computations and they were looking weird, but I was like going on the, I was thinking, oh, then this must be a 16th here and a 16th here. So a total of an 1/8 removed. And then the next one would be a 64th removed. But I don't think that's actually the case. Do you see the problem that I'm having? Like why it's not as nice? Because then at this point, all right, we're gonna continue on this fourth. This isn't what I wanted to do today, but this is what we're gonna freaking at least do for a short while here. So I removed alpha, the initial step, and then at this step, I removed the total length times alpha. I scaled it by alpha. And then this must be how much I'm removing from here. But this, so how much is left? Maybe that'll look intuitive. So if I've got 1/2 minus alpha over 2, and then I remove this, minus alpha plus alpha squared over 2. I don't see how that helps me with anything. That's what's left. Christian, did you say you did some work on this?
I tried.
You tried, yeah. Was this the issue you were coming up with, or?
The issue that I kept having was like I think I was thinking of it too much in terms of like where the endpoints were.
Yeah.
And then I couldn't really get it to match up with what the like set we did with the third looked like.
Yeah, fair enough.
But yeah, I got really confused on this really quickly and it kind of just like devolved.
Yeah, I hear you. I think let's hold off on that problem. I'm gonna go think about this more carefully before. I know I've done this some point in my past, but this is all feeling a little ambiguous right now. So hold off on that one, please. Does that sound okay? Or dig into it. It could be extra credit for like something you've missed in the past. Just any work you do on this, it doesn't have to like resolve it, but if you do some work on it, because I'm gonna do some work on it. But definitely not gonna spend the 75 minutes floundering up here. Guess I'll leave that in the video. Yes, I will. All right, I was kind of thinking we should have at least one more quiz, maybe two. Does that sound okay? Two more, probably, seems about right. How about, I was gonna say next Wednesday, but, yeah, let's do Wednesday. I think we can do this. There's only one new definition. Are you okay with learning one definition between now and Wednesday? It would actually be helpful. I'm getting vague yeses and then no response from two people. Okay, that's a very ambiguous head shake. Okay, I'm gonna take it as a yes, because that's a convenient answer for me. So let's do a quick quiz on Wednesday. And again, just definitions. So definition of an open set, closed set, compact set. And for compact set, there's these different characterizations. So there's the sequential, and that is any sequence in the set. A set is compact if any sequence inside the set has a convergent subsequence. So sequential definition, the open cover definition, it is compact if any open cover has a finite subcover. Be sure to understand what this is. So also there's like two parts here, right? You need to understand the definition of open cover, but also like what is an open cover and what is a subcover. You have to understand those to understand that definition. And then the last one was the Heine-Borel. What was Heine-Borel? What's the other characterization of a compact set? It was the first one I put up.
That was the one where it was closed and bounded.
Yeah.
Compact.
So yes, so Heine-Borel says that these definitions, either of these, is equivalent to closed and bounded. So if a set is closed and bounded in the real numbers, in n-dimensional real space, these two things also hold. And then the last one that I wanted to just put on there, this is from today and I'm about to do it, is a continuous function. I'm very excited because we're finally getting into functions today. This is where things get really a lot weirder, really awesomely weird.
So this quiz is next class or next?
Yeah, so let's talk about it. Does Wednesday sound okay, or do you want to wait till next Monday? You tell me. Christian, what's your vote?
I could do Wednesday.
You could do Wednesday, but you could also do Monday?
Yeah.
Camila, what would you prefer?
I think Wednesday.
Think Wednesday?
Wednesday.
This ambiguous?
Wednesday's fine.
Okay, okay, cool. Okay. Liv, you okay with Wednesday? If one person's not, I'm happily move it to Monday. Okay, all right, we'll do this on Wednesday then. Just quick definitions. So today, on towards the continuity. We're gonna do a quick review of functions. Continuity. Yeah, not much better. Continuity. So first off, we have to remember functions. It's been a while. So I've got a function f. What is a function? Mathy friends. What's a function? Just any, there's lots of ways this could go.
It's I guess like a structure that gives you an output, like one output for a given input.
Yeah, that sounds like pretty good. So I like that you said structure. That's a very mathy thing to say. Yeah, it's a rule or a formula, a structure. It's or maybe it doesn't even have that, and we're just thinking about it in the abstract. But function f, we say f of x takes input. I like the way you said that. Input x and returns output f of x, and this denotes the output for a given input. Cool. What is the domain of a function? DOM, we're going to use that. What is the domain of f?
Inputs,
What's that?
at the set of inputs.
Set of inputs, yeah. Was that what you were going to say? Yeah. So, so this is the set of all valid inputs. And sometimes we're not told this, and we use what's called the natural domain. So the natural domain of a function equals all x such that f of x is defined. So you wouldn't have a place where you'd have division by 0 or the square root of a negative, all those kind of basic things we don't want to do in math. That's just called the natural domain. But sometimes we have an artificial domain that someone has restricted. Maybe this is an application and x can only take on certain values. So sometimes this natural domain is cut down into something that makes sense for the problem or whatever we have at hand. Let's see, so sometimes we'll use this notation. We can say x goes to f of x. So sometimes this is just a notation that we can use that's very suggestive. Notation. That just means that f is the rule that this arrow is taking. This looks a little pedantic that I've got f in 2 places, but this notation is quite well used. So for us, f will map from some subset D of the real numbers into the real numbers. So this D here will be the domain. It might be the natural domain, but it's a collection. It might be all of R too, we don't know. This is, do you remember what this is called from Logic and Proof? What that output space is called? It's not the range. Do you remember? Codomain, does that sound? Yeah, it's like a weird word. So this is the codomain. So our codomain will always be reals. We're always spitting out real numbers. We're always taking in real numbers. It just might not be all the real numbers. So today's about continuity. So let's actually talk about continuity and understand why we're going to make the rule the way we make it. So let's go to some graphs of the function. So you've got x and your f of x here. And this is your inputs, and this is your outputs. And I know you know all this stuff. I'm just saying it again. So what if I have a function that looks like this? That is, let's say that point is x not there. What does that mean? What is the meaning of the word?
I was gonna say x naught's not included in the domain.
Yeah, exactly. It's not defined at x naught. So this right here is f is not defined at x naught. We don't know what its value is. This doesn't feel continuous. We want continuity to feel like no breaks. That's really what we want, no breaks in the graph. We want that feel, and we're going to mathematize it. So it's going to be cool, because this is a weird idea. Let's look at another example. So what about this? Now I've got that doesn't look continuous. How would you explain the difficulty?
I was gonna say it's not smooth, but I don't really think that's the right word.
It's not smooth, that's true. But we're not thinking about differentiability.
Yeah.
Cease, do you have something? Like, what does it feel like is wrong there? it's not continuous?
Yeah.
Yeah. So like just in plain words, what do you see there that feels like how would you explain to someone what's going on there? Doesn't have to be super mathy. Is the function defined at x naught?
Yes.
It is, yeah, it's defined. But it's not filling that hole there. Right, so that feels, how could I think about what this value is? And I'm gonna pull the heat off Cecil real quick here. Like, how do you figure out what value is being approached here?
Take the limit.
Limit, yeah, thinking about limits are about what happened near a point, not at it. So here, what we have is that the limit,
F of x is not equal to.
yeah, does this limit exist based on this picture? It does, yeah, because your fingers, right, you trace in right and left hand limits, you meet the same place as you get close to there. Exists, but is not equal to the value of the function at that point. So that's a hard one. I gave you a hard one to like kind of think and vocalize because you had to think about limits. So that's the problem that's here. What's the problem with this one? We don't want this. We don't want this for continuity. So we're kind of going through all the aberrant things we don't want to happen. What about this one? Camila, what do you think about this one? Like, what is the troubles? What are the troubles there? So is the function defined at x naught? Is there,
Yes.
yeah, that definitely, that solid dot, so we're defined there. What's wrong though?
I want to see the limit of one.
Yeah, absolutely, yeah. The limit from the right side and the left side are not the same, so the limit does not exist here. The limit does exist here. So here, the limit as x approaches x naught of f of x does not exist, even though the function's defined there, right? And the function was defined here. So what we want is a definition that rules out these possibilities. So let's actually go to the first definition that the book gives us, and then we'll talk about equivalent forms. So we want, for f, sorry, I'm getting my language. For f to be continuous at a point, x equals x naught, we want three things. One, we want the limit as we approach that point to exist. So I want at least this. Two, I want f of x naught to be defined. So I don't want that. I don't want a hole with no dot. But what I do want, and so we don't want this, that's the limit exists part, that rules this out. But with both these, I could still have this scenario. So the last equivalent, or the last statement we want here is that the limit exists, the function is defined, and the function and the limit are the same value. So, and then the last one here is limit as x approaches x naught of f of x equals f of x naught. So as you get close to the point, the output matches the output at the point. And the cool thing is, this actually says all three, so you really just need that definition right there. So let's put that up. And let's actually write this in a different, I think we need to write this in a sequential way. So, formally, f that maps from some domain in the reals to R is continuous at x naught, which is a point in the domain, if for every sequence x sub n in the domain that converges to that point. So that would be sequences here, like x1, x2, x3, sequences of points that are converging to that point we're interested in. It follows that f of x sub n, so the function values on those sequence points converges to f of x naught. So in other words, you've got this sequence of points converging to this point in the domain, and then the sequence values corresponding on the function. So if this is x1, here's f of x1. If this is x2, here's f of x2. That the sequence of dots here converges to the value of the function at that point. That if I take dots in, take a sequence in the domain converging to x naught, that the image of that sequence converges to the image of x naught. So there's a sequence of points on the graph that still converges to that point. So let's take a look over here and see what would be wrong with each of these. Here we got this one. Here's a sequence of points converging to x naught, and I look at the graph up here. What's the problem? What's the problem here? This sequence of points is converging to x naught, and here's the f of x n's on the graph. What's the problem?
Oh, there is no f of x naught to convert.
There's nothing to converge to here. So simply, even just writing this says this is defined. To simply write, to even say that f of x naught is a place we can go, means this is defined. Right here. Has to be to write it. And then what about here? Take a look here. We take a sequence of points converging to the point in the domain. Here's the sequence of points up here. They converge to this value here, but that's not the value of the function at that point. So this wouldn't hold true. And then here, the limit doesn't even exist for the function. So if I take x of n converging this way, and the sequence of points converging this way, again, this one, there's no limit on those points. If I came in on this side, well, notice that this says for every sequence. So there might be some where it works. It's just got to be true for every single one of them. Because if I take a sequence that goes like this, back and forth, then I'm going to get function values up here that kind of bounce back and forth and never settle down. So that for every is what kind of rules out that case right there. Okay, let's take a look at, do we want to look at some examples? Probably before I get onto the heavy definition here. Yeah, let's actually do a quick proof using this method. And I do have an assignment for you, but I'll just hold off, give it to you on Wednesday. Unless you want it now, I'm happy to give it to you. Just let me know. Prove that f of x equals x cubed plus 2 is continuous at x equals 0. Say x not equals 0. We know this thing's continuous, right? It's just a good old cubic shifted up. We know what this thing looks like. It's just a cubic that goes through 2. We know that's continuous, but we're going to try to prove it with this. So let's let x sub n be a sequence. And the domain here, what's the natural domain? Can you divide by 0? No. Is there a square root? No. There are logs? No. There's nothing weird. There's not a single number you can't do this to and get another number out. So here the natural domain is all of R. That's the domain of F. I'm going to let x sub n be a sequence in R, the natural domain, converging to 0. Now, so I've got this x sub n converging to 0. I'll just write it out like that. So what is f of x sub n? So now I'm going to compute this, and what I'm hoping is that this converges to f of 0. So I'm going to write out here, question mark, does that converge to f of 0? If so, then this is continuous there. So this is what we're going to check. And the check is pretty simple. So first thing you write out, notice that f of x sub n is x sub n cubed plus 2. Just plugging it into the formula. And now I want to take the limit of this. So the limit, as n goes to infinity, of x cubed plus 2, x sub n cubed plus 2, is this. Now I'm just going to use basic limit properties. And these are probably in the book. I don't know exactly what page. But basic limit properties say that this limit is just limit of x sub n itself cubed. Take the limit inside the cube or after, doesn't really matter. And then this is a constant, so it's just 2. So we're writing down really obvious things, but we are making them formal. So the limit of x sub n is 0. So that's 0 cubed plus 2, and that's just 2. And that is equal to the function value at 0. So really simple, seems kind of silly, but let me show you how it's very useful for some, yeah, let's look at our first really pathological thing. So let's take a look at a really cool example. You're going to want to remember this example. This is called the Dirichlet function. There's a couple varieties of this, but it looks like this. I think we usually use a delta of x is equal to 1 if x is rational, and it's equal to 0 if x is irrational. So this thing can't be drawn. We can't draw this. We can imagine kind of what it looks like, but only in the vaguest parts of our imagination, because we know how the rationals and irrationals are just intertwined, right, in a very complicated way. We know there's more irrationals than there are rationals. Those are uncountable. These are countable. So they're both infinite numbers of them, but there's a lot more, infinitely many more of these than the infinity of these that already exists. So what we could see here is that we've got a function that's 0 everywhere there's an irrational number. So we just make this kind of a hazy line here. And it's got holes everywhere. Everywhere there is a rational number, there's a hole down here. And everywhere there's a rational number, there's a 1 up here. So there's a cloud up here as well. So these are all equals 1, where x is rational. equals 0, where x is irrational. So the question is this function continuous anywhere? It sure doesn't feel like it is. In fact, this function is nowhere continuous. There's not a single place in this function where there's a stretch where things don't jump around. So this is maybe your first example of ever seeing it, but this function is nowhere continuous. And we're going to use our definition that we just looked at. So let's prove this. Let's let x naught be irrational. What would be a weird sequence? So x naught, let's say, so x naught is irrational right here. And so what is f of x naught? 0, because it's an irrational. So it's definitely like right there. This definition that we had of continuity had to be true. So I have to be able to get to 0 no matter how I approach this on the graph. What would be a terrible approach to x naught? So it's an irrational. Tell me a terrible way to approach it. So if x, let's say x naught is square root of 2. Yeah, if we only approach on the rationals. Remember how, and we've seen this a couple times. Every irrational is just the limit of a sequence of rationals, every irrational. So x naught is irrational by the density of Q in R. We can find a sequence of rationals that converge to it. Just take the decimal expansion and truncate it. Just move further and further out. We can find x sub n, which is completely contained in the rationals, that converges to this terrible beast. Well, what is f of x sub n? What is the value of the function on the sequence points? What's that? 1. Yeah. Because these are all rational. So this is 1 for every n. So I've got a sequence that's constantly 1. It can't converge to the value at that point. So f of x sub n is equal to 1 for every n, and that does not converge to 0, which is the value of the function at that point. And can you see how we could do this with if x naught was rational, what would we do here? X naught is rational, so in case 2, x naught is rational. So f of x naught is equal to 1. How could I screw this up? What's a bad approach here? Give me a sequence of irrationals that converges to x naught. Start giving you some hints here. What could I add here that gets smaller and smaller but is irrational?
Root 2 over n.
Yeah, I like it. This is irrational. We've proved this before, right? A rational plus an irrational is irrational. So this right here is irrational. But we also know it converges to x naught as n goes to infinity. And the problem here is that f of x sub n then is going to be 0. And that does not converge to 1, which is our value of our function. So this function, using that sequential definition, is easy to show it's not continuous anymore. 2 lines of fuzz. One's a little heavier than the other. So that's kind of cool. I think let's tweak that example a little bit. So how about this one? F of x equals x if x is rational, and it equals 0 if x is irrational. So I'm tweaking it a little bit. I have to go pee. Sorry. But take a minute. Is this function continuous anywhere? I would try to draw a little sketch. Got any ideas?
I'm still trying, if you want to be irrational.
Okay, good. Yeah, yeah. It's good to see some drawing a picture, super helpful. I'll actually just put your homework up, but you're probably gonna need Wednesday's lecture, but you can always read ahead for the motivated. You don't have the Cantor problem anymore. That's my problem now. Let's say, can we shoot for next Monday? Try. Let's just say next Monday today. I think this will be a good amount of time. that's it.
Yeah.
Yeah, got the drawing.
It's continuous where X is irrational.
Oh, interesting. I don't know if we have that one, but, cause that's cool, that's a good one, and that is one, that's called Thomae's function.
Okay.
Which is, well, we gotta bring that one in, cause it's insane, but, so your picture, so I've seen this picture a lot, got a bunch of dots here. So this is, we're 0 when we're irrational, but then we are, and that continues this way. And we're equal to x, so we're basically on the line y equals x. Anytime we have a rational number. So it's like the two lines before, but now they're crossed. So if I pick what were you saying, Cormac, any irrational, or did you say any rational?
Any rational.
Okay, cool. So let's pick a rational out here. So if I'm at x naught and that's rational, then f of x naught is up here. But can you see how I could approach this with just purely irrationals? So I could approach this point with pure irrationals and stay on this line here, unfortunately. The function values would all be 0 there. Does that make sense?
Yeah.
So not there, but what about here? What about at this point? So think about how you can approach this point here. So I'll kind of like, the punchline is that this is continuous only at one point, only at 0. Because as you approach 0, no matter how you approach it, the fact that this top line and this bottom line are coming together means that your sequence will eventually converge to 0, no matter how you approach this. So if you approached on pure irrationals, if you approach on pure rationals, you're kind of approaching on this line. If you approach on pure irrationals, you're approaching on that line. And if you approach on a mix of them, you're just gonna maybe have this oscillating sequence that eventually still converges to 0. So that's like our next step up, and we can call it there for today. Yeah, I'll write up some stuff on that Cantor function between now and then. Has everybody got their assignment too written down? Cool, take a photo, yeah. Oh, also, Dr. Sawyer, it needs someone to help with Mobius strips this weekend. He's doing like a 2-hour activity. It's on Sunday, it's Science Sunday. Is anyone available to go help him make Mobius strips with kids? Cool. All right, no pressure from me. But I did say I would ask. It's the whole coming in on the weekend part. It's a little